Okay everybody, welcome to the first video of the year. This is section 1.5, analyzing graphs of functions, and so hopefully you found this in the SharePoint site okay. Make sure when I'm done here to take the survey at the end. It's on the same place in the SharePoint site. Here are our objectives for today. We have a lot of vocabulary to go through that I want to actually show you what it means versus just tell you, and so these are things that we want to learn, and so we're going to just get going right away here because I want to keep these videos relatively short. So let's talk about domain and range. This is something we've already talked about in Algebra 1 and Algebra 2. Remember, the domain is all of the x values that can go in the function. Okay, all of the x values. Think of these as all of the inputs to the function that can put in. If I look on the x-axis here for this function, now this function that I have graphed to the right here, this is f of x equals x squared, and we're going to be using this for almost all of our notes today. Now your notes that you should be taking along with this one, it look more like a Word document that have a bunch of different boxes in it, but each one of these slides corresponds to one of those boxes in your Word document. So make sure to follow along on that. Alright, and so our first box we have is domain and range, and again, as I said, the domain is all of the x values for a function. And for this one, f of x equals x squared, if I go all along that x-axis, it looks like I could put in any value of x and still be able to square it or get something out for our y values. So for this entire x-axis, no matter what value I put into the function, I can square that. So we would say for this particular function down here, the domain of the function f of x equals x squared would be all real numbers. Now in Algebra 2 we did something like this. X is all real numbers such that x, there's no restrictions, so we would say that's all real numbers. But in this class we want to say that in interval notation, if you remember from yesterday, we talked a little bit about interval notation. We'd have an open parentheses and go from negative infinity to positive infinity, because that is the interval on the x-axis that we cover of possible x values I can put in there. Now let's talk about range. You should remember from last year or any other class that the range is all of the y values or all the outputs. Okay, all the outputs of the function. Now this is probably going to be more limited because you could put in whatever value you want for x here into this function or into other functions, but you might not get all of the possible y values on the y-axis, okay? And so for this one in particular, let's talk about this function's range for y, or f of x equals x squared. And then last year in Algebra 2, we'd write something like this. Y is all real numbers, except if you notice the very lowest point on this function that we touch, the lowest y value that we get, I'll mark with a big black dot here, is 0. Okay, and so we'd write last year the range of this function, or in Algebra 2, we'd write y is all real numbers such that y is greater than or equal to 0. And we have the equal to because we include that 0 point. However, this year in PreCalculus, we're going to use this interval notation that would include 0 with a closed bracket and go all the way to positive infinity, because you could see that I could keep squaring numbers, and as they get bigger and bigger and bigger, I'm going to keep on going up on the y-axis. Okay, remember, domain is all the x values which you put into the function, range is all the y values that you get out of the function. Let's talk about function notation. Now this is something we've been using a lot. It's exactly what I wrote before. We have f of x, and you're going to call the function f. That's the name of the function. Okay, so you might have another name for the function g of x, and h of x, and this one's called f of x. Now x is going to be called the input, whatever we're putting into the function. That is our x values. Our domain are all of our inputs. And then it's going to spit something out of that function. I'm just going to call it y. And that is going to be our output, all right? Because that's what comes out of the function, all right? And so the function notation simply just looks like this. It's f of x equals, g of x equals something, okay? And so let's practice with this particular function here. And like I said before, f of x equals x squared on this graph. And so we're going to use that one to demonstrate what function notation is. So let's look at f of 2 for this particular function. F of 2, it says to take this input 2 and square it. So take 2 squared, that is 4. Look at f of negative 2. That means we're going to take negative 2 as the input, square that, and get 4. Then we're going to put in, let's try 8. Okay, if we put in 8, so you have 8 squared. That's going to be 64. So notice I know what to do for this function based on what the rule is. And my rule that I've set out before, f of x equals x squared. Let's talk about f of something we don't know. Okay, let's just say f of heart. All right. F of heart would just be to take whatever heart was, if it's a real number, and we'd square that, okay? And so I don't know what that looks like. I'm loveless, so I can't really evaluate that. So it'd just be heart squared. All right, and that's function notation. You take something, you put it in, and you spit something back out. And the f is just the name. You can use other letters if you want. Let's talk about the vertical line test. Okay, the vertical line test. That just determines whether something is a function. So for your notes, it determines whether a relation or some other, relationship is a function. And so you should remember this one, because the name kind of says it all. You draw a vertical line. You take your pencil or pen or whatever writing instrument you're using. I'm going to draw a vertical line. How many times does it hit? Now there's a pass and a fail, just like you either pass and fail in Mr. Levis's class. So the pass to determine what's a function. It is a function with a vertical line test if it hits only once. Okay, so it hits only once. Notice on this function, I could remove this vertical line, this purple vertical line. I'm going to take that and move it over, and no matter where that vertical line is, I'm only going to touch this red function once. And again, the red function, of course, the same function we had graphed previously, f of x equals x squared. And we could see that f of x equals x squared passes the vertical line test, because no matter where that purple line is, like I said, I can move this wherever I want, and it's only going to touch that function once. Okay, and I'm going to mark with a highlighter here. It only touches about right there. Okay, now it fails, just like you'd fail in Mr. Levis's class if you don't watch these videos, is that it hits 2 or more times. So 2 or more times. And so I'm going to give you an example here. This could be something like x equals y squared, or y equals the square root of x would be an example of a function that fails the vertical line test. Because if you could see here, if I do x equals y squared, or y equals the square root of x, it's the same thing. Notice that if I draw both sides of it, it's going to fail the vertical line test. If I take this purple line from before and move it down here, notice that I touched twice, okay, and that's a problem. So that's what it looks like to fail, and that would not be a good function. Intervals of decreasing or increasing. I say that wrong every time. I notice it says increasing to decreasing. All right, and so we're going to talk about this particular function one more time, f of x equals x squared. We're talking about when it's increasing or decreasing. Now, the important part, this is something that almost every student has trouble with and that I usually have to mark stuff wrong on, is that we only want the intervals of x values, so only x values. Okay, and so we're looking for intervals here. That should be your key hint that says that I don't care what the function or the y values are, I just want the x values. Alright, so in this case, we want to know when is this function increasing or decreasing. What it means to decrease is as I go right, I will go down. What it means to increase is as I go right, I will go up. Now as I go from left to right here, I'm riding the roller coaster. It starts up here, it's going down, I'm decreasing all the way down until I get to this point here, and then all of a sudden I stop, it looks like, it's this black dot, and then all of a sudden I start to go up. Okay, I start to ride the roller coaster all the way back up. Now, if I'm looking for the intervals, I'm going to say it's decreasing in the green stuff. It's decreasing for the interval of negative infinity all the way to the very left, and it stops when it gets to 0. Notice that black dot on the x-axis, it stops right at 0. And these are the x values. I'm going from negative 6, and I keep on going all the way to 0. It's decreasing. It gets to 0. Now, do I include the 0 in the interval? You have to ask yourself, at that point, is the function increasing or decreasing? Well, it's impossible to tell. It's at that one point. We don't know whether it's going up or down at that particular point, so we cannot classify it as decreasing or increasing. We're going to use an open bracket. And then, all of a sudden, as soon as we move just a little bit past the 0 on the right side, I start to go up. It's going to keep on increasing indefinitely when I go right on the x-axis. And again, these are only intervals of x values. All right. Relative or local maximums and minimums. Now, we use relative and local interchangeably. That just means that these are the relative or local spots, not absolute, maximums or minimums, but we can just identify at certain points. Now, these are really important. Just like on the last slide, we had that one point here, this black dot. That was really important. That's a turning point. It went from decreasing to increasing, and those are going to be where your local maximums and minimums are at. So I'm going to label that same point down here. I notice I went from decreasing all the way to 0, and boom, it starts to turn. These are going to be your peaks or valleys. Peaks or valleys, okay? And obviously the peaks are going to be the maximums, because you're going to go from increasing to decreasing, so from plus to minus, and then valleys are going to be the minimums, which means that you're going to go from decreasing to increasing. And notice that this one, I'm decreasing, I go down, then all of a sudden I turn around and start going up. Okay, and so that would make this a relative minimum. Okay, and so when we're identifying this, again, this function is f of x equals x squared, the relative extrema, or the relative minimum, would be at x equals 0, or you could put the point notation, the coordinate notation, 0, 0. Either one is acceptable for relative maximums and minimums. So either x equals 0 or the point 0, 0. Let's talk about average rate of change. Now, average rate of change is just simply slope. We've talked about this in Algebra 1 and Algebra 2. It's slope, but you're probably thinking, well, Mr. Lovelace, this is not a straight line. We can't find the slope. But I'm going to ask you to find the average rate of change between two particular points on the slope, because even though the rate of change is not constant, it looks like it's steeper over here, for instance, than it is down here, we can find the average rate of change between those 2 points and draw a straight line. And so the one that I'm going to use as an example here is, let's say, between x equals 1 and x equals 3. Okay? And I'm actually going to erase that. I don't want you to think that's something that goes in the box. I'm going to put that over here. So again, f of x equals x squared. It's the function we're going to do this example on. And let's go between, what's the average rate of change between our x value of 1 and x value of 3? I want to know how, on average, how much is this function changing between those two x values? And it's as simple as evaluating the function at those two x values. So if I go from 1 on the function, it looks like my point is 1, 1. Okay, 1, 1. And of course, that is just as simple as saying, well, 1 squared is 1. If I go to 3, 3 squared is 9, so my point is 3, 9, because I put in 3 and I got out 9 as the output for squaring it. Now to find the average rate of change between those 2 points, which I'll represent with a green line here, okay, I'll draw a green line between those 2 points. Alright, to do that, I'm just going to go ahead and use the same old slope formula that you know and love. You take y2 minus y1, so 9 minus 1, those are the 2 y values. Take the 2 x values, 3 minus 1, and you get 8 divided by 2, and that would get you 4. So the average rate of change, the slope of this green line here, is 4. Slope of 4. And that is on average how much that function is changing between those 2 points. Now if you were to isolate and zoom in on any one of these points along the way, your slope might be different at that exact point, and that's a really big calculus idea that we'll talk about later. But for right now, we just want the average rate of change between 2 points. Even and odd functions. This one is a very confusing part of it, and so I'll slow down a little bit for this, and if you need to rewind and replay this, I encourage you to do that. Let's go over it. And so an even function, this is a new concept, has symmetry to the y-axis. So from geometry and trig even, you might have talked about this before too, symmetry to the x-axis, which means that if I have a function value, f of x, that should be the same thing. You should get the same thing out if you put in the opposite value of x into the function. All right? And so let's look at this particular example, f of x equals x squared. Notice that if I put in 3, I get 3 squared or 9. But if I put in negative 3, f equals negative 3, I get negative 3 squared, which, surprise, is also 9. Now what this looks like visually, if I go over to 3, 9, there's my point, 3, 9. Notice if I draw a line straight through the y-axis, there's a corresponding point on the other side, negative 3, positive 9. And that means it's an even function, has symmetry to the y-axis. Let's talk about an odd function. Now an odd function is more complicated. It's symmetric to the origin. Okay, so what I mean by that, algebraically, is if I take f of x and I add the function value of the opposite, f of negative x, it should equal 0. And so I'm going to give you an example of that down here in purple. Let's do the function f of x equals x cubed. Okay, and so I'll sketch that really quickly. You should remember this either from trig or algebra 2 or another algebra class. It looks something like this. And notice that it's symmetric to the origin. So if I pick a point, let's do 2, 8 or something right up here. I'm just going to guess it's 2, 8. Now notice if I reflect around if I go reflect over the origin, which is just like 2 flips, flip over the y-axis, flip over the x-axis, notice I'm right back down here at negative 2, negative 8. And algebraically, if you want to look at that, you take negative 2 cubed, that is negative 8. If I add that to 2 cubed, which is positive 8, I get 0. So negative 8 minus 8, sorry, plus negative 8, just to have that, it should be 0. Alright, that's even odd functions. Again, if you need to rewind and replay that or look somewhere else on the internet, I'd encourage you to do that. We'll go over that more in class. Zeros, roots, solutions, x-intercepts. We've done this a ton too, and nothing mind-blowing here, but again, this is just wherever you touch the x-axis. So touch x-axis, that's the visual way of talking about it. It's when the function of value of x is 0. Those are really the way we look at that. And so in this case, for the f of x equals x squared, you can see right here, there's just 1, 0, okay? and that is at 0, 0. So I could write 0, 0. I write x equals 0. That is a 0 of the function, or a root of the solution, or root of the function, excuse me. It's also a solution. X equals 0 is the solution of the function. If I'm looking for zeros and roots and x-intercepts, I'm going to be looking for coordinates. If I'm looking for solutions, solutions would be x equals. Think that you find solutions to equations, and so it needs to be x equals something. What is the solution? The solution is when x equals 0. If I'm looking for zeros of a function, well, the 0, 0, 0. The root of the function is 0, 0. The x-intercept, when we're talking about a visual thing, we use the coordinates, 0, 0. The last thing we're going to do here today is, this is just corresponding to your note sheet as well, is that we have two columns, okay? We have two different functions, g of x and h of x. Again, these are just different names for functions. Just because it's not an f doesn't mean it's not a function. But we're going to check all those things. We're going to go through. And so your homework for tonight is going to be go through the second column. But before we do that, I'm going to go through the first column for this particular function, g of x. Now, you can't read that in the middle. At least I can't. It's really small. But on your piece of paper, hopefully you can see that as x cubed minus x is that rule. And it says here that, you know, we're broken up this domain of this function. It's a step function or interval or piecewise function. There's a bunch of different names for it. It says that when x is less than -2, right here, if x is less than -2, we use the function value -6. If x is between -2 and +2 inclusive, we use this particular function rule. If x is greater than 2, I use that +6. So let's talk about the domain and range. Now, even though the domain is broken up into 3 distinct intervals between -infinity and -2, between -2 and +2, and from 2 to +infinity, we know that the domain is still going to be all real numbers. And so it goes from -infinity to +infinity. Okay, because it's broken up, but you could still put in any value of x, and you'll get something out, depending on what it is. The range of the function is a little bit more complicated. You could see that the lowest point that the function has is down here at -6, and then it goes up a little bit, swoops back down, comes up, and then boom, up at the top at +6. So the range of the function goes between -6 and +6. All right, and so that's just where the y values are. Even though we have a straight line, it doesn't go above or below those 2 points, 6 and -6. Function notation, again, we're just evaluating the function for these particular x values. When x is 1, we use the second interval, because 1 is between -2 and +2. And so we use the rule 1 cubed, okay, minus 1. Okay, so I just plug that into the equation there. And so I get 1 cubed is 1, minus 1 is 0. Now -1, again, -1 is between -2 and +2, so use that middle rule. And so we have -1 cubed, which is -1. Okay, minus a -1, which again is 0. Okay, and so that's better. And then we have those two evaluated. Now -2 is tricky because -2 is right on the boundary between the first and the second interval. But notice that up here, I'm going to erase these marks for a second. And notice I'm going to highlight right here in yellow that this particular greater than or equal to sign has a line under it. So we actually use the second rule. So again, we're going to have -2 cubed minus a -2. Again, -2 cubed, of course, is -8. Minus a -2 means a +2, so we have -6. Okay, and you can see that visually. It's right down there. G of 10, we have to use the third rule, which is just 6, because 10 is greater than 2, so we have to use that rule. And remember, 10 is our input, and the input is the domain. And it says that when the input is greater than 2 in this function, g of x, we have the function value 6. Vertical line test. All right, let's do that quickly. I'm going to draw a vertical line. You can see that no matter where I draw this vertical line, I could drape that wherever I want to go, and I'm only going to touch this function at one point. So this one passes. It is a good function. Woohoo. Notice my excitement. Are you excited? Are you pumped? I'm pumped. Intervals of increasing or decreasing. All right, and so this is the tricky part because we have a lot of swoops in this one. Remember, we're looking for when, as we go right, we're going up. And so you can notice, I'll highlight in orange, from here to here, it looks like we're increasing. But then all of a sudden, we get to this little peak. All right, and we start decreasing. I'm going to use that with red because I'm sad. We're decreasing. And then all of a sudden, we stop decreasing and start increasing again. This is a pretty good roller coaster. So again, I'm going to use orange, and we're going to go up. And notice, on either side of these two orange parts, we have just flat lines. It's not increasing or decreasing. So we're not going to include those in our increasing or decreasing intervals. I'm only looking at the orange and red stuff. So the orange is obviously increasing because you're going up on the roller coaster. So the intervals of increasing, if you scroll back up again, sorry if I'm making you dizzy here, but we're going from, looks like the x value of -2 to, it looks like -1/2 about. So I'm going to say -2 to -1/2, that function is in the orange zone, it's increasing. And then it starts decreasing a little bit, but it starts increasing again at +1/2. And so I'll write +1/2, and it looks like it stops increasing at +2, because that's when you get that flat line. So I have 2 intervals of increasing here, because I started increasing on 2 different intervals. Pretty self-explanatory. And then between those 2 orange intervals, I'm decreasing, so between -1/2 and +1/2, I am decreasing. Alright, and if these don't make sense to you, I mean, you need to go ahead and plug those in and see if those are the points where we start, you know, you could verify it algebraically or with your graphing calculator whether those make sense. Relative or local maximums and minimums occur between intervals of increasing and decreasing. So you could see up, it's where these black dots are. We have one relative peak, which is a maximum at -1/2. So it'd be a -1/2. It looks like the function value at that point is right around 1/2. So -1/2 is a max. And then you have another min, which is a valley at +1/2. Excuse me one sec. 1/2, it looks like -1/2 is the y value. Because you can see here it dips down. I'm talking about that point right there, 1/2 of -1/2. That's a min. All right, average rate of change. We're looking from -2 to +2. Well, the value at -2 is -6, and the value at +2 is +6. And so we can just use the slope function. So we have -6 minus, excuse me, we're going to go from the other points. We're going to do +6 minus the -6. And you have 2 minus the -2. And so again, you're going to get 12 over 4, which again is 3. All right. That's the average rate of change between those 2 points. Even odd functions, it certainly isn't even because you could see there's no symmetry on the x-axis, but you could check the symmetry about the origin. And you could see here that it's not always true if I'm correct here. Let's take a look here. Yep, no, actually would be. It's symmetric to the origin, and so we'll see that verifying algebraically. Okay, so if we take f of, let's say -2, does that, if I add that to f of +2, well, I get 0. Well, f of -2 is -6, f of +2 is 6. That's 0, and you can verify that. This one's going to be odd. Any zeros, roots, or solutions? Yep, it touches 3 times. Looks at x equals -1. X equals 0 and x equals 1. If you want those points again, you just put them in the notation -1, 0. This is coordinate notation, excuse me. So 0, 0, and we have 1, 0. All right, and so that's the video for today. Make sure that you fill out the second column for your homework, and I'll be checking that tomorrow. If you have any questions, be sure to hit me up on Twitter or email or anything else, and I will see you tomorrow. Have a great night.